Good evening, everyone. And let me start by welcoming the audience first and the participants to another seminar talk in this seminar series organized by the Al School of Business. This time, together with the Center of Advanced Mathematical Science and the graduate program in computational science, we're extremely thrilled to have with us Professor Margot Gerritsen. Did I pronounce it correctly? All right, from Stanford. So I went to her website and I noticed that she's a very proud Dutch, so I had to mention it. Margot was born in Netherlands after receiving her MS degree in applied mathematics at the University of Delft. Then she moved to the US in search of hillier and sunnier places. Again, I copy-pasted this. And I can confirm that it's indeed a hillier and sunnier place. In '96, she received her PhD in scientific computing and computational mathematics at Stanford. And before returning to Stanford in 2001, when she had a nearly 5 years time in Auckland, New Zealand, so a global charters. She's today a professor in the Department of Energy Resource Engineering at Stanford, interested in computer simulation and mathematical analysis of engineering and natural processes. I think she's going to be talking also what she will be doing, so all these words will become much more living and clear to you in a minute. From 2010 to 2018, she directed the Institute for Computational Mathematical Engineering at Stanford. Since 2015, she's the Senior Associate Dean for Educational Affairs in the School of Earth. I'm always impressed to see a very productive researcher and an extremely also efficient administrator. I don't know how you do it, but that's for another time. She's also something very dear to her heart. She's also the co-director and co-founder of Women in Data Science. You probably heard about that because Lama does lead a version of that here at OSB. And she's the host of the WIDS podcast as well. Sarah, maybe you can tell us a little bit about her research before we start.
Thanks a lot, Victor, and thank you all for being with us this evening and morning, probably in West Coast times. I also want to especially thank Victor for leaving me the easy task of pronouncing the title of Margot's presentation, which goes like, "Nu breekt mijn klomp." Maybe I said it right, maybe not. 40 years in computational mathematics. So I'll leave it to her to correct my pronunciation and explain the expression. Margot's interests include sustainability and renewable and fossil energy production. In addition, she's involved in coastal ocean dynamics, yacht design, as well as several areas of computational mathematics, including search algorithm and matrix computation. Her most recent projects include traffic congestion and emission simulation and mitigation, and wildland fire prediction and mitigation. I should also mention that Margot kindly accepted to keep the talk quite casual, and hence feel free to ask questions by raising hands, or if you feel like typing your question in the chat box. Also, some heads up that the talk will be recorded and it's going to be posted on the YouTube channel of the Center for Advanced Mathematical Science. So probably we'll follow up with the link for all the participants who are present with us this evening. So thanks again, Margot, thanks again, Lama, and for everyone for being here and for the organizer for bringing this lovely speaker with the overarching topics that she's going to be talking to us about. So Margot, thanks again, and the floor is yours.
Thank you so much, Victor and Sarah, and of course, Lama, for inviting me to this seminar. I was just in Amsterdam virtually, but I'm really logging in here from Bend in Oregon. I'm on sabbatical, so I'm not at Stanford right now, but still West Coast, and it's still morning here. So I blame every mistake that I make today on the early morning or early-ish morning. But thanks again. It's a pleasure to be here. You were very good with the pronunciation of the title. Nou breekt mijn klomp, which in Dutch means something like "what just happened?" And it's an expression of surprise. And in my time as a STEM person, which is now almost 40 years, I've used that expression many, many times, because we've gone through, and we are actually in a little bit of what we call a maelstrom, you know, a very, very fast flowing current when it comes to computational sciences, where things change extremely fast. And in the last 40 years, you know, the domain of computational sciences have changed so much. And I'd like to talk a little bit about that today, both in terms of the challenges that we have outstanding for us. And of course, I cannot leave data science of that, because it's one of the reasons why we're in such turmoil right now. And I hope that this seminar appeals to all of you, at least partially. I know there's a very diverse audience, but feel free to ask questions and interrupt. As Sarah was saying, we're a small group, and interactions are very welcome, and it would be fun for me as well. Before we start, I'd love to do a quick check with the audience, because I'm really interested in how many students are here. So if you're a student, please put a reaction in your little video by either putting your thumbs up or waving your hand or do something. So all students, please. Okay, great. 4, 5. That's wonderful. 6. Okay, so more. Okay, that's great. Thanks so much for doing that. Who is here from, who has a background in computational sciences? So again, just put something. Oh, I like that, Wasim, your party emoji. All right. So who considers him or her or themselves a pure business person? Okay, so there are a few people like that. Well, I know very little about business. so we'll see. If you have any questions about how things relate possibly to business, or you're interested in potentially looking at AI or other data science approaches for business purposes, and have questions about that, then I'm very, very happy to connect with you person to person. The reason that I'm interested is that I do quite a bit of consulting as data scientist to business, and discuss what is hype and what is not, and what some interesting directions could be for business applications. But they're often so very specific that is better to talk about this one-on-one. So please feel free to reach out to me. So let me share my screen, and I wanted to start just talking a little bit and giving you a little bit of background of what I've done. And so can you see this okay?
Yes.
Yep, great, wonderful. And I'll make sure that I'll put the chat up as well, so I can follow that. Okay, so as Victor was saying, I grew up in the Netherlands, and yes, I am still sort of a proud Dutchie, but I also have spent so much time in the United States, more time than I've ever been in Holland. That of course, the United States is really now my home country. I moved to the States in now 31 years ago, and did my PhD at Stanford University. I never thought, by the way, that I would ever get out of the area where I grew up. I grew up as a girl in a very small village in the Netherlands, and for the life of me, didn't think that I would ever be in California. So that was a real surprise, and it was certainly not planned. And that has really been sort of the roadmap of my life, that most of the things that I've done were unplanned. And so I'll talk a little bit about that later, because I see so many, particularly students, trying to optimize choices to allow them to reach a certain goal. I never did any optimization, but I just took opportunities in front of me, and it's been just a whirlwind, really, because after the PhD at Stanford, I moved to New Zealand, and I spent 5 years there. And I thought for most of the time in those 5 years that I would never leave it. But lo and behold, 5 years later, I actually found myself back at Stanford, and doing something that I was never trained to do, really, from the outset. So I trained as a mathematician, And I trained in the time, though, that computer science really was taking off. And so this is in the 80s. In 84, I touched my first computer and spent a long time figuring out how to actually turn it on. So this is how much of a computer scientist I was at the time. But it was a really interesting period because computer science and any application associated with that really took off. And that really generated my interest in going from more theoretical mathematics, which I studied as a student, so in the early 80s, to much more applied mathematics and ultimately to engineering applications. So here's a bit of a timeline. So I started studying quite theoretical mathematics. I got very interested in one particular application in computational mathematics, which was computational fluid dynamics. And I applied fluid dynamics to various areas. I did coastal ocean research. I looked at more theoretical aspects of fluid dynamics for a while as well, and sort of model flows, if you like. And then I started going into some esoteric applications. One of them, for example, the design of sails for a competitive yacht. This was for the America's Cup. If there are any sailors amongst you, you may know about this. And then when I was pulled back into Stanford, I joined the then Department of Petroleum Engineering, and we changed our name to Energy Resources Engineering. But for quite a long time, I was working in fluid flow below the surface, so reservoir modeling, and mostly for the oil and gas industry, mostly around mitigation of harmful environmental impacts of oil and gas and trying to attenuate or reduce these harmful impacts. But I think my craziest project was related to fluid flow indirectly, and that was the design of a aircraft, or well, aircraft is called Herky, which was a replica of a pterodactyl for National Geographic. And if you're interested in that crazy application, there is a documentary that National Geographic made called Sky Monsters that now came out 16 years ago, 15 years ago. And you can see me in that documentary leading a team of engineers who built this flying replica of a pterosaur. And we were more or less successful. And of course, as a good drama, they show all the unsuccessful bits much more than they show the successful bits. But then over time, you know, I like I said, I trained as a theoretical mathematician. I've done many different applications or applied myself, and maybe also because every couple of years I get interested in something new. And I think my foundational underpinnings in math and physics really allows me to relatively quickly change application area. Of course, I feel like a complete fake for the first year or two whenever I dive into something new. But it's amazing how much application areas have in common. So yes, most of these applications I've talked about have been in fluid flow, but I've also spent in the last 15 years quite a lot of my time on data science applications. Now policy advice for decommissioning of internal combustion engine and adoption of EV engine vehicles. I've also done things like wind turbine placement optimization, and many other applications, from genome detection to building search engines for the Library of Congress in the United States. And what has been incredible for me over all those years is to see how many of these applications really rely on the same kind of mathematics. One of my mentors used to say that ultimately every application you look at, whether that's in business or in fluid dynamics or in weather prediction, climate modeling, you name it, optimization, data science, ultimately it is all linear algebra. And I found that to be true to a large extent. And so one of the pieces of advice for you students on the call is to really think about foundational mathematics and statistics, because once you master those to some extent, you can be quite agile if you have a love of learning of new areas as well. And I'd love to chat more with you about this if you have any questions. So anyway, I've been all over the place, really, but seemingly, but below all of this, underneath it, the engine has really always been the same. And what's interesting is that these challenges that I saw mathematically or computationally 40 years ago or 30 years ago or 20 years ago are still there, and they're being kept alive because of very rapid changes in hardware and software solutions. But before I go into that, let me just share with you a little video of one of the applications that I like the most, and it also gives me this opportunity to bring you or beam you up to the San Francisco Bay Area. So Stanford University is around here. San Francisco is just at the bottom of this highlighted circle. And here you're looking at a fluid flow simulation of tidal flow in and out of the bay, where the colors indicate the magnitude of the tidal flow velocity. So these are here averaged out over the depth. And we did this simulation, or colleagues of mine did this simulation with software that I was working on with friends for quite some time. And I'm showing this because when I was a student in the 80s, there was absolutely no way that we could do something like this. So this really came thanks to this advance in compute power, and of course also in algorithmic developments. Very intriguing flows this, where you have fresh water from rivers coming up in the northeast corner of this larger map, flowing into the bay, and then salt water moving in and out. Very, very high tidal flows here in the Golden Gate. So we've had lots of fun doing this, but it did take probably around, well, let me see, maybe 20 people years to develop a code like this and to be able to do the simulation. So very complex and very intriguing. Now we do this, for those of you not familiar with how these sort of simulations work, by approximating physical laws that we have on, how fluid flow behaves, how pressures at different locations in the ocean and in the bay waters, and vary with depth, depend on neighboring pressures and so on, and how pressure differences then move water, and how gravity comes into play and things like that. So all those physical laws that we know, we translate that, we approximate these with relations between pressure, water velocity, density, salinity, at a discrete set of points. So we're approximating these physical laws that hold in a continuous manner by discretizing. And in every vertex of these triangles here, and this is little averaged out a little bit, and it seems a lot bigger, this what we call grid, and the number of points seem to be a lot less than we use in reality, because we refine this very, very much in especially this area, if you can see my cursor in the middle, where there's so much going on. And we get out of that a set of relations between all of these different quantities at these vertices. And these sets of relations we linearize, and it becomes just a one big system of equations. And for those of you familiar with linear algebra, of course, that means matrix computations. And really all the complexity of the physics, it translates into properties of this large system of equations, and all the challenges associated with the physics, non-linearity, which means very fast possible changes with small perturbations, very intricate balances of pressure, very fast changes when boundary conditions, so for example, tidal motion or sea level rise changes, which we input in the model. All of this is reflected in this big system of equations. And by studying the system, by studying this linear algebra, we can really understand a lot about the physics. So I love this translation of physics into mathematical entities and mathematical relationships and matrix algebra in the end.
Margot, quick question.
Yeah.
So as you were talking about this, and not that we have to bring an application in business, but I was thinking, like, are there some studies similar, for example, in the world of finance about, for example, trade, financial trades, for example, or the volume that is happening that could actually be similar to this kind of flow of
yeah, absolutely. There's a lot of business or quantitative finance models that rely on similar type of approaches. And I've worked on one or two projects like this with colleagues at Stanford. We were looking at behavior in the stock market, for example, a lot of people using partial differential equations to model their behavior. And then to solve for those systems, you would use a very similar technique. Now, those systems, as you well know, are often even more complex and nonlinear and unpredictable, right? So that brings its own challenges, and there's a lot of uncertainty associated with these systems as well. So that brings in this whole area of stochastic simulation, where you're trying to accommodate and model the inherent uncertainty. What has been so interesting is that the advances made on uncertainty quantification in the financial markets, and you can understand that these are very well supported by companies that make a lot of money in that space, have trickled back to PDE community and fluid flow, and we're using some of the approaches that came out of the financial market analyses now in fluid dynamics as well. So there is a, when I said, hey, all these different areas, they really rely on the same sort of mathematical building blocks underneath. What that also means is that you can have this cross-fertilization, if you like, between different streams of science and engineering. And one of the most interesting things for me in the last so many years, maybe 15 years, is that synthesis of ideas and this cross-fertilization is much happening at a much higher rate than when I was a student, and simply because of the internet, because of how easy it is now to discover work done in other domains, and it was very much harder when I was a student. So it took me about 15 years, for example, to realize that a method that people had been using in human biology was very much appropriate for something that I wanted to do in cell design. It sounds completely silly, but when I found that, I really managed to advance my own research a lot. So this is the wonderful thing about the internet now, is that we can do that so much faster. Mm-hmm. So the other thing that, of course, has made a big difference in my work and in work in general is just the number of tools that we have available to us. And I always like putting this in perspective. Now, for those of you who grew up sort of on the left side, so with very minimal desk, when I was a student, my desk sort of looked like it was on the right side. And it's incredible how much faster we can now do things and communicate with each other. And I bring this up particularly because of the communication, as I just said, that it's just so much better. Some people argue that there are other things that are now impeding us and slowing us down. The sheer number of emails, for example, we get, the assumption that we can be in virtual meetings all the time, and the demands on our time have also changed as a result of it. But there are many, many positive developments in these last years, and I really don't know how we did things in the 70s and the early 80s without Wikipedia, without other online references. There's so much knowledge at your fingertips. It's really wonderful. That also has a very negative outcome to most students, and that's why I mention it, and I'll talk about this a little bit later, is this idea there's so much knowledge out there now that you don't know, that it makes people sometimes a little anxious. So we'll talk about this in a little bit. Now, the other thing that's of course been unbelievable, and I put this slide up because every time I look at it baffles me, is how fast compute speed has changed over this time as well. And I know I sound a bit like a grandma to talk about, well, when I was young, everything was a lot slower, but I'm really not that old, right? I'm 55. I feel like I'm still only 30. And when I look back on the last 35 or 40 years in STEM, I'm thinking, whoa, how did this happen? And of course, with this incredible increase in compute time, what it meant is that we can do so much more in our computational field. And sometimes we get a little bit arrogant, and we think that because we can solve very large problems now, we can really understand things a lot better. And that's not always the case, which I will talk about in just a few slides. Now, the other thing that has happened over time, which is also interesting and sometimes a little bit stressful, is the incredible change in the software as well. So it's not just the hardware, but it's also the software. And for those of you in computational sciences, maybe you found this just like I found it a little bit difficult, because it's very hard to stay on top of everything. So when I started, I had a typewriter and a Casio calculator. And then I learned Pascal. And then for a very, very long time, actually, for about 20 something years, I used Fortran 77. And for a very, very long time, I used MATLAB and a little bit of C or C++. But it was stable for quite some time. Sort of in the 90s, in that period, I understood those tools, I mastered those tools, I used them a lot, and things were not moving all that rapidly. But in the last 15 years or so, we've seen this just unbelievable development of new kinds of computing paradigms, new kinds of computers, multi-core, GPU, different kinds of supercomputers, map-reduced type systems for data science, Spark technology. New languages come up like CUDA, Hadoop, Python, Julia R, and it is really hard to keep on top of that, particularly as maybe as an older academic or researcher. So I don't know any of those languages really very well that my students are now programming in. And I really have to rely on students to pick up these sort of new technologies, because I simply don't have the time to keep up. This also means that more and more of our time in the computational science area, and no doubt this is also the case in the business school, you spend a lot of time just keeping up with new developments. People get very excited about this. There are business opportunities, of course, plenty to develop these sort of new tools, and they're heavily promoted. And some of the commercial companies like NVIDIA, but also companies like Facebook and Google really have a lot of power in this field and setting those trends. If those companies start taking up some of these new technologies, we almost have no choice but to follow. But it's much easier for commercial companies and big companies to change and adapt, because they have so many more resources than it is for us in the research community. And I really consider this a bit of a threat to research nowadays. So Ibrahim, yes, it is that the constant change of software can be very inefficient. It can also help, but overall, I'm not finding it really advancing progress all that much. Sometimes there is a change that has a really big impact, and for example, emphasizing here the change of the use of graphics cards for accelerating computations. And so the GPU hardware really has made a tremendous difference, because it allowed us also in the computational world to take relatively simple operations that are part of any large computations and to accelerate them very fast on these graphics cards. And I think that has really been a big shift in our ability to understand some processes. But like I said, we spend so much time rewriting and redesigning algorithms and software for new architectures that keeps us also alive and well. Sometimes people say, numerical analysis, linear algebra is dead. We don't need to do anything in that anymore. We understand how it works, and we understand all these algorithms, and we have everything we need to build our applications. But it's wrong, because every time a hardware changes, the way that you have to implement algorithms change. And very often that means that you have to understand algorithms in a different way and really redesign them too. But in any case, overall that time, that I've here described, computational mathematics really took off. And there were several things, right? One is that we had so much more compute power, so people could do a lot more with computational mathematics and simulate and predict and optimize. And then what happened is that algorithms were published, they were made much more accessible than in the past. Public domain softwares were written. Now we've always had public domain softwares through big national laboratories, for example, but they were really not that accessible to many people outside. In the last 25 years or so, it's really been quite recent that public domain softwares were written by with relatively easy user interfaces that allowed people to quickly pick up a software package and apply it to a domain. Now that has many risks associated as well, and sometimes we call it, there are a lot of cowboys out there, we say, meaning that there are a lot of people who just use these off-the-shelf packages without really understanding what's in it, and they apply it to various challenges and then claim that they can generate solutions without really understanding if the solutions that they're generating are really useful or not. But it has also meant, of course, an opening up and, if you'd like, a democratization of computational mathematics. And really it led to this enormous boom in computational math. And I'm putting this here for two reasons. One is that we are in a similar phase right now with data science. And so I'll talk about this in a minute. And two is it comes with a big challenge. And in the 90s, one of the challenges associated with that is that people just take software without understanding what's really in the software. So without understanding the black box, the algorithms, the data that they were generating, the data that they were analyzing, of course, there is a big business risk associated with that. So for those of you at the business school, this is something that a lot of industries are struggling with big time now when it comes to data science. They're hiring a lot of computer scientists, data science, so-called data science experts who are using algorithms for business applications without really understanding. Now, in the 90s, one of the industries that really got burned by the then advances in computational mathematics and the proliferation of this public domain software was Boeing. Boeing, very, very large and influential company at the time in the United States, really at the forefront of computational mathematics development, together with national labs like NASA and Lawrence Livermore and Sandia Labs. And people at Boeing found that the engineers they were hiring really weren't very good because they didn't understand what was in the softwares that they were using. And so Boeing, led by a wonderful person called Jim McMasters, then really tried to, and they were successful, change the US engineering education. So imagine a company like this going back to hundreds of US engineering colleges and reforming their engineering education, which was quite something. And they felt the need because of this this change that also led earlier to a lot of these engineering colleges say, oh, we don't need to teach the fundamentals anymore because we have all this software available to us that has basically encapsulated all of that knowledge. And so all the students need to know really is how to run this. And I think we're at a similarly dangerous time now when it comes to data science.
Margot, there's a question from George that is related to this point.
Yeah.
He wrote it as well, but he had risen his hand. So George, do you want to ask a question?
George, very nice. Yeah, main difference between older and the newer language. There is not so much of a difference. One of the big things is that most of the new software packages that are out there, I don't even call them languages so much anymore. They come with built-in tools that make it so much easier for people to do some standard or standardized algorithms or computations faster without having to write it themselves. So if you look at how we used to code things in Fortran 77, you know, most of the codes that we build, we had to implement all of the algorithms ourselves, you know, sort of from the ground up. Then comes a programming environment like MATLAB that has a lot of built-in tools already, and so that made it much easier to start implementing and prototyping. But MATLAB is not for very high, industrial computations, right? Because it's simply not fast enough. It's parallelizable now, but it certainly wasn't when we started using MATLAB, so it's not as effective. So, but new tools that are out there now typically come, no, this is the case with CUDA, this is the case with Python, this is the case with R and Julia, come with algorithms readily available, either because people put that in GitHub nowadays and say, hey, if you programming in Julia, here's a package that does this optimization routine, or because the developers of these languages push for that themselves and hire people to actually create these building blocks ready-made. And there is tremendous advantage to that, but there's also, again, this danger that people are using programming languages with built-in algorithms without really understanding how these algorithms have been calibrated. So we often see people use linear algebra building blocks, for example, without understanding the default parameters set in these algorithms, which can really affect the efficiency of the algorithms for their particular application.
Right, I see. That makes perfect sense.
Yeah.
Thank you.
There's another question. No, from
yeah, I will actually address this in a little bit. So I will leave that for now, and I will come back to that if I need to.
I'll let you manage that.
Yeah. So in any case, what happened at the time in the 90s, and I'm putting this up because I think we need something like this now for data science, is that people really became aware of this risk and said, hey, we need comparative solution projects. We need to keep the practitioners honest. We need to establish best practices. We need to establish minimal QA and QC for publications. We need to be open about mistakes that we make and redesign, as I say, this education and training. And with companies, for those of you in the business community, you know, one of the things that happened in the 90s, when you look at this, companies did something. He said, oh, we need to jump on this trend of computational mathematics. We need to outsource this because we don't have in-house capacity for this, but there are all these companies out there who can do this for us. But then many of them got burned, and many of them, as a result, started building in-house capacity. We are now in data science at the position or at this place where companies are outsourcing. And some companies are now getting burned, and some companies are so far now that they're starting to build in-house capacity. So it's really interesting to see that same sort of pattern here with the advance of data-driven technologies. Now, the other thing that this increased power and this seemingly increased accuracy and capability that we've created over the years have led to is really more and different kinds of errors that we're making. And let me just, for those of you in computational sciences, give some example. So when you're modeling something, be that the stock market, or be that an ocean flow, or be that a climate model, there are different kinds of errors that you're making. One is a modeling error. So that in the graph is the red curve. And modeling errors, meaning the errors that you're making when you're mapping the physics to the math, or the human behavior to the math, and then you're mapping that onto some discrete model, like I talked about for the San Francisco Bay. That modeling error goes down typically as you're increasing the size, the number of details that you put, the number of physical phenomena that you're trying to model. And you can increase the size when you have a larger supercomputer. So what people have been doing over time is increase the size of this discrete mapping of this discrete model, and they believe that they can drive this modeling error down then, and that should give them more accurate solutions. But unfortunately, what happens at the same time is that compute errors, and you could see this naively maybe as an accumulation of round-off errors. And round-off error accumulation, when you're computing solutions to very large systems, tend to behave in particular ways that have to do also with the type of model that you're looking at, and ultimately are again related to the physics. Compute error increases also with increased size. And there are things called conditioning problems or stability problems, particularly for very strongly nonlinear systems, where the compute error can grow so fast that at some point you're crossing over sort of an optimal point of minimal error. And as you're increasing the size after that, you're not really helping yourself. You're actually introducing more compute error than you're reducing modeling error. And with the increased supercomputing power, we have over the years really gone from the left-hand side of this graph to the right-hand side of this graph. And if you don't understand how these compute errors come about, you don't understand what's really happening in these algorithms, how errors accumulate and also get propagated from parts of your model to another, you miss that extra dark blue curve completely. And you you believe the results that you get, but in reality, you're looking at things that are completely erroneous. This is the era we're in right now with climate models, for example, that there's so much physics put in climate models, and we're driving these climate models to be more and more accurate, looking at smaller and smaller patches of the Earth and zooming in, which of course we'd like to do. We'd like to be able to tell you exactly what the climate is going to be in South Lebanon, over time. But unfortunately, when we're zooming in that much, we're increasing the size of this modeling problem, and we're introducing a lot more error, and we don't really understand that error very well, because it comes from this compute error, not from the modeling error, if this makes sense. So this means that for people in computational mathematics, there is an enormous task, and we're not done. Just having an algorithm that seems to work and that you then put on a large supercomputer doesn't help you very much unless you understand what the error accumulation in those algorithms is. So what people predicted when supercomputing power started increasing is that fundamental applied mathematicians or computational mathematicians like myself would be out of a job because the supercomputing power would solve everything. And instead, we have more and more challenges, maybe of a different nature, but we haven't gone away. And unfortunately, though, because of all this public domain software and this idea that all you need is the software to solve a problem, many students have turned away from this area, are not very motivated to take courses in this area, but you should, right? The other thing that a lot of people do, as I mentioned before, they put more and more physics into their models as well. And here is just one slide that shows you what kind of physics has come into, for example, the climate model, and is very illustrative of this process. And just think about it, the more models you put in, the more errors you're introducing that are then interacting with each other in quite nonlinear ways, and really, really, really hard to understand what this error interaction can actually do. So we sometimes say that we've seen over time an exponential decay in the time required to get to the wrong solution. And we see this also, of course, now in data science. So it's been
can I ask a quick clarifying question?
Yeah.
Just for my own sake.
Yeah.
So when you're talking about the computer error in the previous so correct me if I'm completely off. So in some sense, you're not talking, I mean, obviously there is the time dimension, so it will take much longer for those much scaled system, but you're talking about the error of the algorithm itself. Let's say, for example, a computer that's doing a very simple, I don't know, calculation of x plus y. Now, when you have so many of these kind of terms that you need to add, the algorithm that makes that sum is gonna be some of all these errors that's going to make a difference, while in fact for smaller system it will not make, and it will be very accurate. Is this really what you mean by the computer error?
Yeah, absolutely. So it's the accumulation of the error that you're making because of roundoff in your computer.
Okay. Yeah.
But that can be exacerbated, that can be worsened by the way that you're designing your algorithm. So sometimes, there are approaches that can help you a little bit with that. So if you really understand how algorithms work and how roundoff error accumulates, and there are many areas in computational mathematics called perturbation studies or perturbation analysis, where you can understand that a little bit better. And you can also understand how to rewrite your algorithm to minimize as much as possible this roundoff error accumulation. So that's a really important area of research. And that means that for some applications, you cannot use the algorithms off the shelf because they may not have that integrity that you're really hoping for. You could also go to high precision computers, as Fatima is saying here on the chat, but that only works to some extent, right? So depending on the size of the problem, you can probably alleviate some of this compute error by being very smart about what algorithms you use. So you need expert advice on that. And by going to, for example, high precision compute. Now, if you, of course, doing high precision computing where the individual roundoff errors are smaller, your whole simulation will take much longer. Okay, so most of the time people would like, are so tempted to look at bigger and bigger and bigger problems. And there really is this tendency to do more and more and more and more, and they forget about this. And that some size of problems, even the high precision computers cannot really give you what you want. Now, there are bespoke software packages and bespoke companies that really focus on these high fidelity simulations, and they have high precision compute hardware. They really focus very closely on these algorithms. But most of the public domain softwares that you have there that people are very tempted to use do not have that sort of sophistication. Now, I wanted to just mention the other challenge that we're seeing right now, and this is this move to data-driven decision-making and data-driven research. Which has come with its own challenges again. So I don't have to tell you this, that we're creating, generating, collecting enormous amounts of data, not just on social media, but also through Earth observing systems, for example, ground penetrating radar, you name it, through satellites and in all kinds of other ways. So a lot of data is available. We've seen data penetrate the science and the business communities big time. And we went really in the last 40 years from data supporting our efforts and informing models to actually having models that are purely data driven. So where we're skipping the step from physical or human behavior modeling, mapping onto mathematical models, mapping onto discrete models, and we go directly to data driven models. It's an enormously big market, of course, right? Everybody's jumping on it, everybody's using it, and it's a little bit of a déjà vu. And I've mentioned that before. Now, some people think that data-driven models are the answer to everything. In fact, there are colleagues of mine in computer science who make very strong claims where they think that all domains will really soon be a subdomain of computer science because of it. But I absolutely disagree with this. And I think this is the computer science. Some computer scientists say this because they're in this hype stage, which we were also at the start of this computational mathematics revolution. And people are going to get burned, and they're going to understand that no, if you want to make a data-driven decision, then really it will remain an absolutely so community effort, and you must have the domain expert. Because the reason for that is, of course, the question always comes first, and the design of the solution approach needs to really understand, the underlying processes that you're trying to model. You cannot just look at data. Data can be highly flawed, can be highly biased. And of course, you need to spend a lot of time interrogating the data. One of the things I'm seeing now is that a lot of people say, if we just have a lot of data and we have an off-the-shelf software package with the latest and greatest, maybe a deep neural network, then we can solve everything. And again, it makes me think about 25 years ago. And so sometimes what I see in my head is a baby Bam Bam here from the Flintstones, if you know about this, where people take a big club, which is a deep neural network, and they hammer happily on any problem they can find. But it doesn't always give you a good solution. So it's so important in this area to really think very hard about what you can and cannot do within this data-driven world. So now I'm being a little bit of a grandma talking about this, but here are some questions that I'm taking my students through and companies that I consult for, etc. And many people, because they're so excited to have data and just take a tool that sounds incredibly good and sophisticated and then just apply, they don't really think about this. So what I see at this stage is, again, very reminiscent of 25 years ago, but also has its own challenges. And some of the data-related challenges are, people find it really difficult sometimes to understand the difference between calibration, how you can always fit a data model to what you're expecting the outcome to be versus true prediction, where maybe you can actually get surprised by some of the outcomes. I always very, very superstitious or suspicious, not superstitious, suspicious of papers or people that claim or that say, look, the data model that I've designed does exactly as we thought it should. We're often wrong about our prediction about behaviors, and so that's not a good sign, but a lot of people see this as a trust expression. Another thing that I see is that a lot of people feel that just more data will make the algorithm better, which is not the case for very similar reasons as what we've seen before in computational sciences, but also because a lot of the time, even if you have more data, the actual data richness does not increase. So what's really important is to understand what is unique about the data, and just having more of the same data doesn't, of course, always make an algorithm better. We see also in data science, many people look at patterns that are really phantom patterns or relations that are not really there, but they come up in the data, and they're found in the data because of the patterns that we tell the computer systems to look for. And this phantom pattern problem is a big one in many applications, particularly when we're using data-driven approaches to simulate natural processes. And for this, of course, you need to have the domain experts to tell you, what is phantom and what could be real. So we can do away with domain expertise. And there's a lot of bias and ethical problems. And this is very clear when you're looking at newspaper articles, right? A lot of people are so incredibly worried about some of the applications because this problem is that people believe what comes out and apply it way too fast. Now, another thing that has happened is, when I talked about the advent of computational mathematics, I mentioned NASA. I mentioned very large established companies like Boeing, who were themselves doing a lot of research. But I mentioned national laboratories a lot and universities. And one of the things that is happening now with the data area is that most of the research that's out there, and certainly most of the research that people talk about and the softwares that are available have been developed at private companies. And so these private companies, they own data, they own this software, they're driving development. And they're doing this in a particular direction, and people are just using it, often willy-nilly. Things that were developed in Facebook, for example, or Netflix, in terms of recommender systems, used for recommender systems in other business areas where they really may not be very suitable. So there's a lot of that. There's a lot of problems with bias, as we've seen. So Nabil is asking really nice questions related to this richness. Are there tools to check, measure if data is rich? Absolutely, and those are tools that you can use in data mining. But really, it's a very complex problem, right? To see, is a data set rich? Because it means that you have to interrogate that data set. You have to look for patterns. You have to look for anomalies, and it really is detective work to some extent. And most people just simply don't take the time. And one of the reasons for it is just what I said, is that so many of the developments nowadays are driven by commercial companies for whom it behooves to come up with solutions fast, to be the first to do something, because there's a commercial benefit to that. And so very, very often when you have software algorithms really driven by commercial companies, it's too hastily done, right? It's too fast. There's not a lot of quality control. It's incredible how much software is out there that people use that really hasn't been tested thoroughly. And one of the reasons for this also is that the companies that are putting this software out and using it, they do not really immediately get penalized for making errors. Now, a Boeing company, as in computational math, of course, would be immediately punished if there was an error in aircraft design software, because then their aircraft could crash. And we've seen an example of that with the 737 MAX. Very interesting example where a company lets go of this very rigorous quality control process that they put in place in the past, is relying on software outsourced, developed by others, and is lost expertise of that software within the company, and that can lead to very devastating consequences. But they're penalized immediately, right, in their pocket, in their revenue. Companies like Facebook and Google and others are very, very rarely punished for bad behavior or for errors in their algorithms, because they don't feel it in their pockets. They're still controlling this space, and there's still so much growth in that space. And even with erroneous software, they can make a lot of money. So there really is no incentive for those companies to be extremely rigorous in the development of these algorithms. And it is those algorithms that other people are picking up. So we have to just be really careful about this. So we are in this stage, as I said, and we really need to establish best practices. Now, I see it's already 7 o'clock your time right now, so that's the formal end of this seminar, and I'm happy to stop here. I'm happy to continue a little bit if you'd like. I'm just checking in with Victor and Sarah here about what you would like to do.
It's up to you. I mean, we can continue for a few more minutes if there is a message you want to, you think.
Right, yeah, I would. Okay, great, wonderful. Let me just talk a little bit about a couple of unintended consequences maybe of this unbelievable surge that we've seen in computational mathematics and data science. So one of the things that I wanted to highlight is that even though many things have changed in the last 40 years, there's some things that have not. And one of the things that hasn't really changed at all, in fact, has gotten worse over time, is the participation of women in this field. And it's incredibly important to me. And here are some stats, and I will just flash them. You can have a quick look at them, because now so much power and therefore, wealth and influence sits in data science, and there's so few women really entering that space, which is why I'm so thankful to all our WITS ambassadors, and particularly Lama and others at AUB for helping us deal with that a little bit. And when you look at the reasons for this, there are really two myths, and particularly for all of you, both women and men on this call, just want to say these myths that are still out there, that are holding a lot of women back, have really been debunked so many times, but it's still part of the culture in many areas. And one myth is that success in this particular field requires and this is, this is essential, a really strong innate ability. And I don't think that's the case. You can have a weak innate ability of very little innate ability and still grow tremendously in this field. But there is this sense that you must be a natural in this field to be successful. And that's, I've seen so many examples in my lifetime where that was not the case. And the other thing, and that's the killer, is that women have less innate ability typically than men. By the way, the same thing is true in finance. In finance, there is this sense also in the culture that women are just not as savvy as men in the business world, and it still is there in so many places that I've seen. So as a result of it, a lot of people, a lot of women and other minorities feel a bit like an imposter and find it really hard to thrive in this environment. And it all starts really early on, right? But we have to get away from this. And, how do we do this? Particularly because being inclusive is really good for everyone. I always, when business leaders ask me, well, why, if I can hire lots of men, if they're available to me, why would I even care about getting more women in? And of course, it's really silly to think that way, because there is incredibly strong talent that they're just ignoring. That's one. But also what we've seen many, many times is that the more diverse teams are to work on problems, the more questions are being asked, and the more thinking outside of the box can really happen. So we're really, really keen on that. And what gets me in data science and computational sciences is there's so many amazing women. I mean, look at your own Lama or your Fatima. So I'll put them up here because they're some of my sheroes, as we say. There's so many of them. So we started Women in Data Science in 2015, really to promote them and to make sure that people knew about this and that this was normalized, that women can do this, are outstanding in their field. And we started with a really kind of a small conference, and now with WITS we're everywhere. But I wanted to emphasize AUB. WITS at AUB is one of our rock stars of WITS, and I've been so incredibly impressed with what your ambassadors and the whole community has put up. So big thank you, particularly because we realize very well that the circumstances in Lebanon have not been great in the last years, and certainly not now. So just a great expression here of gratitude to all of you from the whole team here at Stanford. And there's so many WITS ambassadors everywhere with wonderful stories, which I won't talk too much about. So if you're interested, here's the conference website, witsconference.org, and you can always also email me to talk about it. Now, let me just finish though with something that I've seen in the last decade particularly, and that may be the case for some of your students also, and that's this increased stress, particularly among students, that have a lot to do with some of the things I talked about earlier. One of it is to do with education, and this is very US focused, and I'm curious to see if it resonates with anyone in Lebanon. But we finding it that students are finding it increasingly hard to deal with ambiguity and uncertainty, and that has to do with our high school education, where things are, the ambiguity really has been taken out. And a lot of the time, students are taught there is one way to do something, there's one right answer, there's one approach. And of course, we all know that that's not the case. But they come into university really having to unlearn a lot of that, having to become comfortable with ambiguity and uncertainty that are underneath, of course, and right front and center in so many applications. And here's a lot of the students really therefore struggle with research. So I always think about, why do you do research? It's not to be promoted. It's not to earn a lot of money, but you do research because you'd like to discover things. And while you do research, you cannot do it without making many mistakes. And so this hesitation to make mistakes that I see in many students now, and their fear of making mistakes and their fear of failure, the fear of doing things that are not just exactly right is so much bigger now than it was when I was a student. But of course, you have to realize that the best experts are actually those who've made every possible mistake, right? So that's what I'm saying here. And the other thing that really is very difficult for students sometimes is that they find it really hard that when they're trying to understand an area, they often have many more questions than they get answers. But that is really the beautiful thing, right, about learning. So I see a lot of anxiety, and that it takes students and also colleagues a long time to become comfortable really with this uncomfortable nature of exploration and discovery, but it's also so very beautiful. Okay, so that's just something I wanted to mention. I'm not sure if that resonates with people at AUB, but I've seen that huge problem. And one of the reasons, of course, that people are also stressed is because things are coming at them so much faster and more furiously than 30 years ago or 20 years ago even, right? And as a student particularly, you see so much around you every day that you do not know and you do not understand, and you get this feeling that that you will never be on top of everything, and the answer is no, you won't. But the difference, the disparity between what you don't know and what you know is growing over time. It was easier, I think, for me when I was a student. Yes, I knew there were things I did not know, but I wasn't confronted with this all the time, nor was I entering a work space or an educational space where developments and changes were so rapid. And so agility is the name of the game nowadays, right, for everyone, being able to very quickly learn new things and adopt new tools and successfully adopt them and benefit from them. And to become agile, you need to be a risk taker. You need to not have any risk aversion, really. You need to be courageous enough to jump into new things and to know that you're going to survive, and that's not so easy to do. And you need these foundations. I think if you have strong foundations, agility comes with that too. Anyway, let me just really stop here now, and if there are any more questions from people in the audience, I'd be happy to stay on. I certainly have a little bit more time, but I don't want to keep you here too long.
Thank you, Margot, on these beautiful, actually, concluding remarks. Yes, let's leave it. I mean, if people need to leave because we had planned it until 7, please feel free. But I'm sure most of us would like to stay a little bit longer. If there are some questions, I know I do have one, but I will leave it on the end if there is more time. Please, you can just write your question or unmute and speak out.
Yeah, in the meantime, Margot, I also want to thank you for tying it in very well with the beginning of the lecture, where you started with not looking for optimized paths. They should be kept open for exploration and learning. So I think a lot of our students here, and I know a lot of them are from computational sciences, from physics, they were thinking about the optimal tracks and how is it that we move in learning computational sciences and moving on, and sort of planning it ahead from the start. But I think you're a success story, and you speak for an itinerary which was somehow of random walks, which ended up to be very optimal.
Yeah, and let me permit me to put up one slide that I always like, because this relates to this optimality. So I often find that people, and I was the same maybe in high school, but I quickly learned that it wasn't going to work for me, is that you think that you can optimize, right? And that you can have this smooth linear path between where you're now and where you want to be. Right? And that there is such a path, and all you have to do is optimize and really think very smartly about it, and you can find it. And in fact, there are people out there that claim that they found this, and they're always lying. So just keep that in mind too. But what I find is that the path is more likely this, so it's all over the place, and it's also much more fun. And sometimes it's like this, you think you're going to one goal and you actually end up elsewhere. And sometimes it's like that you that you never get there, but it's also good. So you have to keep that in mind, that life is itself very nonlinear. And if people tell you things like, well, you must do this because otherwise doors will close for you, or if you don't do this, you can never get into this market or that market, always take that with a grain of salt, because it's very seldom the case. And the other thing that I think we suffer from a little bit nowadays, and that's to do with in many parts of the world, and I understand that for you that may not be as great right now, but we've certainly seen an increased mobility of people, and as a result of it, there is this tendency of many to think that the grass is greener elsewhere, right? There is always a better path, and they see this on social media, or they see this on LinkedIn, where people say, oh, this and that, and people seem to be successful, and you feel that you're falling behind, or that you're not as successful. Well, all of this you have to take with a grain of salt, because there's so much self-promotion taking place, right? Also, so people never tell you the whole story. And what I see there is people constantly shift and change their minds in pursuit of this better solution, which is probably not there. And so sometimes, what I've done in my life is I don't credit myself with much. I'm not a mathematical genius. I don't think so. The only thing I credit myself with is that I take an opportunity and then I don't think about it anymore. Then that's what I'll do. And I apply myself, and I don't think too much about all the things that could have, would have, should have, because I don't actually know that anyway. So if you're thinking about, oh, if I only had done this, then now I would have been able to do this. Also just tell yourself, well, I'm wrong about that, because you don't know. What happens in your life is often a sequence of serendipities, a sequence of opportunities that come because of the people you meet, because of the things you read, and you cannot predict that in advance. So all you can do is learn as much as you can, really enjoy the learning process, focus on foundations to help yourself, and then when an opportunity comes up that you seem interested in, you're excited about, why not just take it and see where it leads you, and you never know.
We have questions from the students. I think Ali has his hands raised, George. So Ali, you can unmute yourself if you want.
Okay, so first of all, thank you for this amazing and truly inspirational talk to a certain extent. Well, I actually want to comment about something, that the fear of students to do mistakes does not actually flow from within. It's actually from the culture of the university, that they have to get it right from the first time, otherwise they won't fund the education, and it's all those stuff. So students feel that they have to get it right from the first time.
Yeah, and you make a really good point, Ali. And I mentioned high school. I folded high school. I think this starts actually quite early in many places, but unfortunately, what has happened at university over time, and I see this also at Stanford, is that as students come in, with a different culture, with a different mindset, the university also changes. And unfortunately, we've become also victim to certain metrics and statistics, right? So we've seen this increasing emphasis on pass rates, on other type of metrics that really gets in the way, I think, of pure and simple learning and exploration, right? And we're obsessed with metrics. We're obsessed also, it's the same for faculty. Young faculty often feel they cannot explore. And why? Is because they're chasing a citation index that they need to show as measure of success. And so you're right that the system fails us in this. And so I'm not blaming the student at all. No, I think that this needs to also come from the university. And I still see universities around the world or departments where this sense is very strong of exploration, where they're really trying to get the students to change their mindset, and other universities that have also jumped on that unfortunate bandwagon. So very, very good point, Ali.
Yeah, exactly. So I actually have a question about the computational versus learning models, how the errors, like it can increase with the size of the system. Well, you mentioned that it's a class of ill conditioning problems, and that it's usually a form of a precision problem, and how it's infinite precision, and when we have high precision, it might decrease the problem. So I want to ask you, what are the ways to, or techniques to get over this ill conditioning problem?
Yeah, so this is the you know, if you have a problem with round of error accumulation and this conditioning that I talked about, it is always because of the phenomena and the processes that you've modeled. Now, there are better or worse ways to deal with those models. So you can make the problem of conditioning worse, or the seeming computational error worse, if you don't take care of the algorithm, but you can never remove it. So what you have to do is go back to the problem design. So in climate change, for example, where we see many errors accumulate to the point where we cannot do, there's too much uncertainty in the outcomes that we see now, particularly in these very refined models, right? There's too much uncertainty. And you can, by the way, probe this yourself for anything you do by putting in small perturbations. So suppose that you have a model and you're not sure if you can trust the outcome. One of the litmus tests for this is that you perturb some input parameters or a small thing in the setup of your problem. You can do this in data science, by the way. If you have a neural network that you're using, say, perturb the neural network a little bit, put in some more layers, make the width a little bit bigger, put in more nodes, you know, change the functions that you're using just a little bit, and see if your outcome is very different. Because what these strongly nonlinear systems often have with this ill conditioning is that a perturbation leads to big changes in outcome. So you always can interrogate that a little bit yourself. But if you have a system like that, right, you're saying, oh my goodness, I changed an input data by 1% or 0.1% or 0.01%, and I get a completely different answer, then you have to go back to your model design. You're trying to do too much then, right? So what you can do, and which we do in fluid simulation a lot, to say, okay, I cannot, you know, put in cloud formation models in the climate model. I just cannot do that. I have to interrogate cloud formation in a much smaller scale. So not for the world, not for climate, which is multiple years, right, the simulation, but for a smaller region. So we could sometimes call that a subscale model, right, where you say, okay, I'm going to do it for a particular region, or maybe for an idealized situation, to really understand what happens, and then maybe, you know, accommodate for that behavior that I see, for that new understanding that I have of this smaller sub-process, by tweaking my larger code a little bit. But very often it's just because people are trying to do too much, and they do it. You get tempted to do this because it's a little non-intuitive, right, to say that a model that has more and more detail can actually become less accurate. That a lot of people don't believe that, right? So you split the model into subparts. You're becoming a little bit smarter on what to put in and what not to put in. And what a lot of people are trying to do now also is to say, okay, let's stick with climate models, because most people have some sense of what that means, right? In the climate model, let's take data that we have of climate and put that in as well to help tweak the model a little bit to keep it on track. And there are these techniques called data simulation, where actual data is now put into the model too, to help guide it along and to sort of correct along the way processes or predictions that may go a little wrong because of all this error. And that can help to a certain extent, but usually when you're predicting out, that's not very useful because we don't have the data, of course, of the future. So some of those techniques help, but you just have to be very, very careful with interpreting results of this. Sometimes what you have to do is to say, okay, I have a model that that may give us wrong solutions, particularly if I predict out too far, right? So you have a climate model and you're saying, I'm going to see what happens to southern Lebanon, 20 years from now. You can never make accurate predictions that far out. So sometimes you have to stay a little bit closer in time, stay a little bit smaller in geographical scale, and so on. But again, what it requires is really talking with the people that designed the problem definition from at the start, right? And to say, what did you put into your model? Why did you put it in? Why do you think these processes are critical? Can we leave some out? And that's the only way sometimes to do this. So there's no computational solution to this, really.
That's absolutely interesting. Thank you so much.
You're welcome.
Maybe a last question?
George had a question.
Yes, go ahead.
So yes, hello everyone, and thank you so much again for this amazing presentation. I was really inspired. I wanted to comment on the stress thing among the students. That I'm in my 4th year now of undergrad studies at AUB, and like most of my friends are now obviously younger, and I think that this young generation is actually really stressed about getting grades, like feeling successful with their courses, with their career, and so on. I think this is really rising, especially at AUB, in my major physics and in math, especially. Now on I have like one small comment about the graph where the mathematical modeling would decrease with the size of the model, and while the error will increase. And I wanted to ask if there are any limitations on kind of parallelizing our problems while computing the solutions. So what I mean is, no matter how big our system would get, wouldn't we be able to kind of parallelize like our solutions? Is there a limit to that? And like,
no, you can certainly gain, you can gain a lot of efficiency in the time it takes you to get to the solution by parallelization. The interesting thing is when you're using hardware that allows that, the algorithms often are adapted to that, right? And so the order in which you do computation changes as a result of it, and therefore sometimes the way that the round of error accumulates changes character too. And so that makes it so interesting. There is a lot of work done on the building blocks of linear algebra. Now, I made this claim that linear algebra is underlying almost every application. So, believe me, for a second that's the case. And so you can imagine that people have gotten together and said, oh, because there are some building blocks like doing a matrix vector multiply or computing an inner product, that almost every application in the whole wide world uses. In fact, inner products, if you know inner products, are the most commonly computed thing, right? Google searches are basically just gazillions of inner products, right? So all of the hardware now has been optimized also just to do inner product calculations, which is in itself really interesting. But so people have gotten together and said, well, what we should do then is give the community the building blocks for the building blocks, right? If they want to build an algorithm that solves a system or that optimizes, they need these smaller building blocks. Let's provide that to them. And that's LAPACK, Linear Algebra Pack. And lots of people have worked on this there are thousands of people years put in that software. And every time there's a new architecture, people write dedicated LAPAC, fundamental building blocks for these operations that are really happening at the compute level for each of these architectures. And every time they worry about error propagation in the way that they're implementing it. So all these things can be tailored, right? So one of the things to do is, if you want to use an architecture, is to make sure that there are algorithms like that available, and then you can maybe mitigate some of the possible increased compute errors associated with this architecture. Because if you're using other algorithms that were not designed for that particular hardware, your error propagation can be a little bit mystified, right? I mean, you don't always understand then what's happening. And with the stress, you know, I'm so glad that you bring this up. I see this too, and been trying to work closer to home on this and with colleagues around it. And for all of you in charge of students and assessment, you know, one of the things that I found made a really big difference is that if the faculty themselves and the instructors emphasize the learning and the growing aspect of it, so that they say, hey, in my class, we're here to learn, and this is what I want you to get passionate about. And this is also what I judge. Now, what happened, for example, at Stanford, in many cases still happens, is that people students would enter a class, and right from the very beginning of the class, they were assessed. Okay, so you have your first homework, you get the grade for that, you've got 2 midterms, you've got quizzes, and right from the get-go, they were assessed. And then the final grade would be some sort of average of all of that. Now, what's wrong with that picture? What's wrong is that it gives the students the sense that right from the very first day in this class, they have to be on top of this material. They come in with all kinds of different preparatory backgrounds, right? So some of them already have done courses like this, others have not. But there is no sense in students that they are rewarded for growth in understanding. There is this sense that right from day one, they got to know. And so when in my courses and some of the courses of my colleagues, I changed my assessment strategy to reward growth. So to say, if you're not so good in the beginning, if you take time to warm up, if you're on the learning curve, but really down in the valley, you're not halfway up the learning curve hill yet, that's okay. Because what I'm really interested in is your growth. So I reward that, right? So how do I do that? Well, we have the final exam. If I see improvement over time in the course, I don't put weight at all on what happened in the beginning. When I started doing that, a lot of the students felt more comfortable because they feel, okay, it's okay for me to not be on top of it and to grow. And sometimes, you know, we put, you know, little boot camps together for people that are a little bit rusty. So this also happens a lot, right? That when we're teaching something, say in physics, and we're using math, sometimes forget it's been a couple of years that students have seen that math, and it takes people time to de-rust, right? So you have to give people that time. So that has helped a lot. Departments that put less emphasis on grades when they're admitting people to their department really helps a lot. De-emphasizing the GPA, the average grades that you get, helps a lot. Really also for students to understand that there are so many pathways to success. One of the stresses I see in the United States at high school and also at college, that there is this idea that unless you get in certain schools and unless you make it to certain universities, that you're a failure, which is so sad. You know, I'm at Stanford. Stanford is known to be, you know, a good university in the United States. And so many students say, oh, I want to get into Stanford because then my life will be a good one and I'll be successful. The thing is, you know, I think Stanford is highly overrated. There are hundreds of universities around the United States where you can get an equally good education, right? But we've created also this this idea in many people's head that there are only certain ways to be successful and that you have to get into certain programs, otherwise you cannot make it. And that's just wrong as well, but it is perpetuated. So anyway, just a few more comments, George, to what you were saying. Maybe some of it resonates and others not. But if there is a lot of stress among students, I highly, highly recommend the students and the faculty to get together and talk about this and really acknowledge it, and to see if there are some different ways to look at assessment, different ways to put curriculum together, different ways to allow students to de-rust a little bit and to have things like boot camps, different ways to support each other. It's tough to do in an existing structure of the university, but it is so incredibly important for the health and well-being of the students. We see many stress related diseases and sicknesses among students too at Stanford, and it worries me a great deal.
All right. Thank you so much, Margot. This was, a multi-dimensional talk at all levels. Thanks again. Really, we really appreciate it, and I think it's great that we're recording actually. So those that missed it also can get inspired as well, like those that had the chance to be here. I'll leave my question for another time. I think it's already too late. I mean, maybe too early for you. And then we thanks again. Thank you.
Thank you so much. And
very good.
Yeah, and please feel free to email me as well if you have any additional questions or you want to chat about something. Always happy to climb on the Zoom with somebody and talk a little bit more. So please don't hesitate. Easy to find. Just Google Margot with a T at Stanford and you'll find me.
Thank you again.
So bye, everyone.
Thank you. Bye.
Thank you so much.